Correcto. Y déjame tener aquello. Entonces, ¿hasta cuándo tengo? 1 hora, 50 minutos.
50 minutos. A los 40 te aviso y a los 45
¿Son 50 minutos a partir de cuando empiezo o a partir de 9:30? No, muy bien.
Hello, good morning everyone. Thank you for coming and welcome to the second day of the third week of City Science. It is my great pleasure to introduce Professor François Lebras. He is a professor in the Institute for Physical Sciences of the university, and he is going to talk about correlation matrices and the analysis of financial time series. Thank you.
Well, thank you very much, Max, and we'd like to thank all the organizers for that very kind invitation. So I want to talk about stuff which isn't actually anything that I play a major role in, but I'm somehow the third or fourth person in the group, which I will mention at the end of the talk. And we've worked somewhat on the analysis of correlation matrices in financial time series. So I guess I need to give you a quick description of the various things that I mean. So what are financial time series? That's obvious, but you still want to define concepts a bit. What kind of correlations does one observe there? What use do they have? So since I'm going to talk about a fair body of research that is to some extent speculative, I want to at least start with one use which is completely non-speculative and classical. That's Markowitz's approach to the so-called portfolio problem, which is an important application of correlation matrices. Then I want to show a difficulty with this classical application, which is the fact that you're not given the correlation chiseled in marble, but you have to estimate it from actual data, and that creates a problem with noise, the nature and extent of which I want to discuss, in particular by looking at what happens when a signal is just noise without any correlation. Then you get, of course, correlation matrices, questions of fluctuation. I mean, stuff that fluctuates mimics correlation, and we'll see that these correlation matrices have a lot in common with the financial correlation matrices, which is a tad disturbing. Then I want to speak about the more recent stuff, things like power maps, short time series, how we can quantify the difference between two correlations, specifically in the case of short time series, and how we can classify correlation matrices with short time series in particular. So the whole end of the talk is going to be about short time series, which I'll try to explain why it's a good idea to use short time series, or it's, well, almost unavoidable. Okay, so first of all, what are financial time series? So here are sort of three quantities which you'll find in Yahoo or in other places. In this case, this is General Electric. It's the General Electric stock from 1984, roughly, to 2000. So that shows a fairly substantial piece of record. And you see three quantities. The first is the price of the stock. The second, its logarithm. And the third, what we call the return. So we will dismiss completely the first two and look only at the returns. So let me define what that is and say why we don't take the obvious thing, which is the price. After all, what else is there than making a profit? Well, the point is, of course, that if you had bought General Electric in 1984 and sold it in 2000, it's not obvious that you would have made a profit. Because, of course, you had given away good $1984 and you get back $2,000 dollars, which are not the same thing at all. So there's inflation, there's economic growth, there's lots of things. Fundamentally, a price is something that has a unit, right? Like in physics. We say a length is 3.7 meters, a price is $5.4. Now the meter, in spite of recent changes in the definition, is a reasonably stable object. The dollar is not. So you don't want to have units. One easy way to get rid of units, as anybody knows who does entropy and statistical mechanics, is to put a logarithm, because then the unit becomes an additive constant and you forget it. So that's already an improvement of a price. The logarithm thereof, because the units are logarithms of dollars. No, the units are additive, so you forget that. But you still have this linear growth. And then what you can do is take the derivative. It turns out that the derivative actually kills the linear growth altogether, and the thing averages zero. Somewhat weird, but it's because the time scale of variations of the derivative is much shorter than these decade-long growth. So we have returns which are essentially the derivative of the price divided by the price. So it's a unitless quantity, and that's what we're going to look at. So returns all the time. It's an important detail to keep in mind. We're never going to talk about prices or anything of the kind, always returns. And these returns, well, what correlations do they have? Of course, the one everybody would like to know about is a time correlation. If you know that returns are going to be positive after, say, having been negative, positive, positive, negative, then lots of people believe such kind of nonsense. It's been amply refuted. There is still a controversy as to whether markets are completely rational. That's the Farmer-Schiller controversy. But still, the fact that markets are quite probably not rational does not really imply that one can easily find correlations. This correlation in particular, which you can measure, is negligible except if your tau is really small. So we're going to forget about that. The other correlation are the instantaneous correlations, or at least, well, correlations at the same time. Time is measured in our data in days, so we're not dealing with microseconds nor with really high frequency trading. So if we average over a certain number of days the product of the return on the ICE and on the J stock, then you get a non-zero correlation. And that is not so, it's not something you should now leave the auditorium to place your bets, because it doesn't help you. And that's the reason, in fact, why those correlations are not wiped out. Because you can't really do anything with them, except I'll try and talk about it. So the first and most classical application of these correlations is the portfolio problem, which is something that was devised in the 60s or 70s by Harry Markowitz, for which he got the Nobel Prize. So we can say that it's safely that it's a well-established approach to an important problem. The problem is, if you are going to buy a set of stocks, should you put all your savings in one particular stock, or should you somehow diversify, and in what way and in what sense? So it's clear that everybody who is anybody diversifies because you want to diminish risk. You don't only want to have maximum expected returns, but you also want to have somewhat a variation that is, put it this way, not too large. So if we have expected returns as a function of the stock being given by mu I, and the correlation between any two stocks given by Cij, then if you take a portfolio which is Pi, so I'm assuming for normalization that you're just investing $1, or if you prefer $1 million, it doesn't matter here. So it's normalized to 1. And I'm assuming that you're not short selling, so the PIs are not negative. And then the expectation value of the return is going to be, of course, some PI mu I. And the variance of that return involves the correlation. That's an easy one. I mean, you can just calculate. Okay, so the variance on the returns is this object. So then what do you want to do? You want to maximize some linear combination of E and V. Well, that's mathematics. The condition that PI should be bigger than 0 puts in some convex analysis in, but it's not really a big issue. You know that at least apart from that condition, maximizing V plus E or V minus E or whatever is basically solving a linear system of the type CP equals mu with appropriate coefficients. Yes?
Why do you want to maximize the variance?
No, you want to minimize the variance.
Right.
Well, I mean, because the variance is a good proxy for risk. I mean, if I tell you, I give you a way of getting $1 million plus or minus 1, or $100,000 plus or minus 500,000, which do you choose? It's not always an obvious decision.
Okay, this is the variance between the expected return.
Yeah, it's the it's the variance.
On two different stocks, right?
Yeah.
So they could both win and have they could be uncorrelated and still be profitable or something.
Sure. But the point is, assume, for example, that they are anti-correlated, which is something that happens, right? I mean, IBM and Apple or whatever. I mean, so if they are anti-correlated, having both stocks is a reasonably safe bet, because if one wins, the other loses. So on average, your variance will be small. Now, that, of course, may diminish your average return. So the question is, so surely correlations enter into the variance. I mean, correlations between stocks enter into the variance. That's just a calculation. You take some PI RI squared, and that gives you some PI PJ RI RJ. Take the average, you get the average of RI RJ, which is CIJ. I mean, that's just we can look at it later if you want. But I mean, it's doubtlessly, this is a correct expression for the variance, and you don't like variance. Well, maybe you do, right? I mean, suppose you absolutely have to have $1,600,000 because otherwise they jail you, then it may be a good idea to choose 1,100 plus or minus 500, because that way you at least get where you want to get with finite probability. So there are cases when high variance is desired, but certainly if you're finding a portfolio for a conservative client, you generally want to give negative weight to variance. And so typically you'll average E minus V or A alpha E minus beta V or something like that, where the coefficients depend on the person. So, yeah, exactly. So this is easily solved in terms of the inverse matrix, and standard techniques have been developed for which Markowitz, as I say, got the Nobel Prize in 1990. Okay. So this is a very reasonable approach. It gives sensible results. It tells you should diversify, and it tells you should diversify in things that are reasonably uncorrelated. So you shouldn't buy a portfolio of everything that is telecommunications, but you should probably buy a mixture of everything, including possibly, if you really want to be safe, stuff that is to some extent anti-correlated. So correlations are important. And now here's the problem. Suppose you're given a correlation, you're never given a correlation matrix. That's the point. You estimate a correlation matrix from actual data, and you say, okay, well, I take these averages over long periods of time, look at the eigenvalues, Note that the eigenvalues which are important for the inverse are the low eigenvalues, so we'll have to concentrate on those. And we look what happens, right? So take an example from real data, 400 stock from the Standard & Poor 500 between 91 and 96. Remember that period, not because it's important, remember that it's 5 years. So it's a fairly huge period. It's not, I mean, if you do things like that, you're not going to get very high time resolution. But you need that to get even a reasonably good, reasonably low noise. So let's see what that gives for what the properties are of the estimated, all of that's returns, yes.
Yes, but is it also experimental?
This is fully experimental. This is Standard & Poor 500, 406. So usually when you have work on Standard & Poor 500, you always eliminate those which are not common to the whole period you look at. That's why you will never find a study that has actually 500 stocks of S&P 500. It'll always have a bit less. In this case, it's 406 because this moderately short period, there were 406 that remained throughout. So this is the result of the eigenvalues of the empirical correlation matrix. So you take the averages of the actual returns, so it's a fully experimental procedure to answer your question. You get a matrix which is 406 by 406, so you get 406 eigenvalues. And now I wish I had a pointer that could actually, so let's see. Oh, and so do, which? Well, okay, I can, so this is the, so this is an eigenvalue close to 60. And then these are other eigenvalues. So that's actually a histogram of all eigenvalues of this matrix. You haven't, okay. So we use, it's this button, okay. Yeah. So here you have the largest eigenvalue, which is 60. Here you have a large number of other eigenvalues. Here, or a fair number. Here you show a greatly amplified thing. A large body of eigenvalues are in this sort of continuous hump, which can be fitted by this dark line that you don't see quite well. There's a slightly poorer fit here, but both of those are theoretical fits from something called the Wishart ensemble, which I'll talk about in a second. So you see a number of eigenvalues, maybe a dozen, which clearly lie outside this hump, and then there's this hump. So what is this hump? Well, for once, we have an easy, clear, and unmistakable answer. This hump is noise, and nothing else. So consider n signals consisting of pure noise. So there are no time correlations, and also signal correlation, nothing, pure noise. And you use, of course, if you average the products of these noisy objects, you get a number, you get numbers, you always get numbers. That's the curse of statistics, right? I mean, you always get something. What it means is the question. Now, in this case, of course, you know that it means nothing, which is good. So what are the eigenvalues of a meaningless correlation? That's what we want to study. Well, that's what they look like. This is a 406 by 4, well, this is an ensemble of 50, I think, 406 by 406 matrices, so I took the same thing, over a few thousand days. So exactly the same data as they had before, and you get the same hump. So it's very much the same thing. The the scale may be a bit different. The hump looked a bit thinner, but overall it's the same shape. And in fact, the thick line that was in fact the theoretical result for this. So this was the fit, and you remember that the fit was quite acceptable. So this was the result, proclaimed loudly by Lalou et al., which belonged to Jean-Philippe Bouchot's group, and Pléroux et al., belonging to Gene Stanley. They discovered this essentially simultaneously. So essentially, the body of what you see, anything beyond those dozen eigenvalues, is an exercise in pointlessness. So noise is essential whenever you estimate correlation matrices. That if you're not going to remember anything else, it's something you might take home. So in particular, I mean, you might want to know which part of the spectrum your portfolio advisor is using. Anyway, so the estimation of the correlation matrix is extremely susceptible to noise, in particular for low-lying eigenvalues, which are the ones that are essential for taking the inverse, which is what you must do for portfolio optimization. So the program of estimating the inverse of the correlation matrix meets a challenge. There are actually two interesting ways of meeting this challenge. One was developed by Lalou, which is a very straightforward and simple idea, which I think is very nice. You simply look at you can identify more or less what's the hump and what is outside the hump. You should remember that the hump has two square root singularities which mark the beginning and the end of the hump. So when you fit, you can get a pretty sharp idea of where the random eigenvalues stop. So you take the other eigenvalues and their eigenvectors, and then you can construct with that a correlation matrix in which you simply set everything that you can safely attribute to noise equal to 0. There is, however, an interesting other idea, which I'm going to emphasize, because even though it's much more black magic than anything else, it was developed by Thomas Gour and one of his collaborators. It's called the power map transformation. And this, well, you'll see. So the power map transformation is this. You take a number q, typically between 1 and 2, and you put every single matrix element of your average correlation matrix to the q's power. Now there's a slight bug, because if your number is minus 0.5, you can't easily put it to the q's power if q is fractional. So you put the absolute value to the q's power, but you keep the sign. So really it is magic. I mean, why should you do that? Well, there is an obvious reason, actually. If q is bigger than 1 and less than 2, then you are somehow softly and with no prejudice according to any absolute value of what is an important correlation, but you are emphasizing large numbers and de-emphasizing small. In fact, a related approach, which is to define some kind of cutoff, put everything equal to 0, which is below that cutoff, and everything which is above put equal to, well, keep. I don't need to tell this audience, I guess, about the merits of power laws in that respect. It's obviously a much better way to suppress noise and make the larger numbers stand out a bit. Now, an important property, an important issue, is that once you've done this horrible act upon the correlation matrix, it's not a correlation matrix anymore. It's true that the diagonals are still 1, but among other things, the matrix is no more positive definite. And, okay. So sometimes, as we'll see, if I get there, this is actually a feature rather than it is a bug. Now, let me come So this can be used, and you can actually try to do portfolio analysis and see whether these things work. And indeed, with Q values of the order of 1.6, the group of Thomas Goer has managed to do some quite nice things with that. However, this is not the main focus of my talk, so I'm going to now go on and talk about short series. So, why short series? Why are they important? Well, consider the work of Laloux et al. It was on 5 years. So, 91 to 96. Well, imagine 2003 to 2008, or 2008 to 2013. At least in recent times, or when times are in any way troubled, mixing 5 years is maybe not a good idea, because the first year may be rather different from the fifth. So that's an issue of stationarity, the one I mentioned here. Another way to say the same thing is that often you'd like to know how the market behaves as a function of time. But when you say something as a function of time, you don't really mean time decade by decade, or period of 5 years by period of 5 years. Or maybe some of the more patient among us are willing to settle for that, but many would like knowing how the market is in January, what will it be like in February? And for that, of course, any kind of work with basic periods of 5 years is hopeless. But remember, I mean, the bulk of a 5-year correlation function, of 5 years, is already noise, right? So what's going to happen if we are somehow going to use 20 days, say? 20 days would be roughly reasonable for a month, right? For 4 weeks. So a 20-day period is quite reasonable. It has moderate granularity, so to speak. It has good time resolution. But of course, if you compare 20 days to 5 years, the noise has increased dramatically. And we already saw that the noise in the 5-year period was a major factor. So clearly, we cannot apply such things blindly. So there are two problems with short time series. One is bad statistics, and the other is vanishing eigenvalues. Well, bad statistics I have already tried to make clear. I think I don't need to comment anymore. Of course, if you're going to do anything with short time series, you're going to need to take a very large number of stocks. I mean, if you take 20 days, then you certainly take more than 20 stocks. Say you are dealing with the Standard & Poor's, so you have, say, 400. Well, if you have 400 stocks and 20 days, then those 400 signals of 20 each are linearly dependent, amply so. I mean, generically, any 20 signals can be chosen at random and they're independent, and all the other ones can be generated thereby. So the correlation matrix is going to have, in that case, 380 vanishing eigenvalues. So what do we do with that? Of course, the number 0 doesn't really carry a lot of information. So we may wonder whether anything can be obtained from that. So let me take those two issues one by one. Okay, so first, let me talk about the noise. What can we do about the noise? Well, we can do two things. First, we can diminish the noise by applying, in this case, for example, a 1.6 Q. That is, you put every element of the matrix to the 1.6 power. More accurately, you put the absolute value, etc., keeping the sign. So that already smoothes your statistics. And then you can, if you have a large matrix, you can consider that averaging over all the elements of that large matrix gives you something which has better statistics than each of the elements. That's the law of large numbers, and it works even in economics. So define, for example, the distance between two correlation matrices. In this case, the correlation matrix measured in the time window T1. So here time window is a month, just as I said, 20 days. So Cij T1 is the correlation matrix at T1, the correlation matrix at T2, but the correlation matrices are 400 by 400, or here maybe slightly less. I think here they're less, they're 200 by 200, but still we're talking 40,000 numbers. So if we average 40,000 numbers, if we average the differences, absolute value of, we get a reasonably meaningful number. Question? So how do I show that it's meaningful? Well, this is something that to some extent will display that. These are the years between 85 and 2016. And I calculate this number, the difference between CT1 and CT2 as a function of T1 and T2. So it's a two-variable function, and we're here seeing a color-coded version of this two-variable function. So it's overall rather small, meaning that there's nothing that looks more like a correlation matrix now than a correlation matrix before. So correlation matrices don't change a big deal, except 2008. Well, 2008, 2010, 1987. Well, maybe 1987 doesn't ring a bell for most of you, but for those of us who were there then, it wasn't a good year. So if you look at the orange years, so to speak, they're not good, right? So difference is not good. That's so when a correlation matrix stands out, it usually stands out for a reason, and it stands out for an unsatisfactory reason. So this somehow identifies crises, and it identifies them in a more or less reasonable way. Note that the graph is somehow reasonably smooth. It's sharp, I mean, right? Let me show you a graph without the 1.6. So it's there, but it's significantly less sharp, right? I mean, the blue is less blue. I mean, the matrices are less similar among each other, and the strongly different things are more washed out. So that shows you the advantage of having noise-reduced matrices. That's the epsilon parameter, which you see here. 1 plus epsilon is the Q parameter of noise reduction. Let me just do another example, which is Japan. So the Nikkei index from the same period, 1985 to 2016. January 1985 to December 2016, as we'll see, this is the very same plot, and we see actually a slightly higher density of possible crises, which indicates that the Japanese economy has been indeed in difficulties for somewhat larger time than the US one. Okay?
When you say this is Cij,
yes.
You write that. What is your window of time?
20 days.
Calculate
20 days.
20 days. Okay,
Yeah.
thank you.
So it's a month's window, exactly. Another question that you might have asked, and which is also interesting, is what do I consider as different time windows? So in fact, they overlap, if I remember correctly, by 10 days. So there are more time windows than the total number of days divided by 20. That's a trick in order to get more statistics. You shouldn't overdo that trick. I mean, sometimes people actually make 20 time windows separated by a day. This I do not consider to be good practice, but okay, no. So classifying correlations. Now we have this distance, the zeta distance, which I just defined, which is the average of the absolute value of the difference between theCij's, right? With or without noise reduction, we're going to, there's a lot of pre-processing of the data before one gets to these results that I'm going to show you. I'm not going to enter into the pre-processing details because there are things of which you should not be aware too much of what goes in the making of them. And so there's lots of witchcraft and stuff, which I don't really want to get into. But anyway, we want to cluster correlation matrices for which there are standard algorithms. One is called k-means. So whenever you have a set of points and the distance between those points, you can try to cluster them so that the elements of a cluster are closer than the elements of two clusters. So introducing differences within a set of points. Let me show geometrically one particular instance, which is actually part of the pre-processing stuff. It's a nice example. Look at those points. They are actually two-dimensional points. So the distance there is not the zeta distance, it's the Euclidean distance. And then you are given those points and you ask, can I identify clusters within those points? And here, those among you which are not colorblind, as I am, will be able to identify 8 different colors. And so those are 8 different clusters into which those have been divided by some appropriate algorithm. Who knows? Okay, so now, do you find this cluster division convincing? Well, my color blindness, of course, helps, because I see less clusters, so it may be slightly more convincing. But it's always difficult to say whether a given algorithm actually gives a result that you're comfortable with. Actually, we were not comfortable with that particular division in 8, and we divided that same number of points actually in 4. But I'm just showing you this as a typical example of what the algorithm will lead to. So we did some pre-processing that led to a 2- or 3-dimensional set of points with Euclidean distance, and then we applied this algorithm k-means, which you either know or do not. If you do, okay. If you don't, I'm not going to explain it. But it yields that sort of coloring, right? So this is what it did. This coloring in 8 seemed to us overkill, and we got, in fact, what turned out to be a better coloring in 4, and this is the one I'm going to use later. So this shows you with a minimum of honesty, what the sort of trouble we had doing what we did. Okay, so the data we used were, again, S&P 500, 194 stocks. Those are all the stocks, essentially, that remain common to S&P 500, from 85 to 2016. By the way, there is here, of course, cheating. Yes, I'm glad you agree. Of course, yeah, exactly. I mean, if one of you came from 2046, say, to tell me those companies are going to be around in S&P 500 in 2046, that's information I would like to pay for. I mean, it's really worthwhile. So here I had that information. So I was by no means in the same position as some hapless individual in 1985. So this is important to point out. So 194 stocks in S&P, 165 stocks in Nikkei over the same time period. So we cluster the things, and we get 5 states for Japan, 4 states. So the US result was the result of which I just showed you an 8-colored intermediate stage. So we decided eventually to 4-color it, and these are the 4 states we have. So now these are what? These are, of course, the averages of the 4 states. So I take all the points that have the same color and average them, and then I get this kind of correlation matrices. In this case, some noise averaging was done as well, so epsilon is 0.6. So you see there are basically rather uncorrelated matrices in the first state with some significant anti-correlation, the green stuff or yellow. The second has significant higher correlations and also higher anti-correlations. It's actually, these, by the way, are industry sectors. So with a bit of luck, well, I'm not going to say anything. Often one sees anti-correlation between the energy sector and the rest of the economy. But I would have to be sure that this is indeed what you're seeing in the second state. And there are far less anti-correlations, much more correlation in the third, and yet more in the fourth. The fourth state, oh God. The fourth state is actually a state related to crisis. Okay. So this is, as a function of time, with time resolution of a month, as always, the evolution between the states. So in the upper thing, you go from 1, 2, 3, and 4, somewhat randomly. Let me show you quickly. This is the transition matrix, basically, from the 4 states of the US. So you see that from state S1, you go to S2 11% of the time, whereas you go back to S1 87% of the time. Maybe the interesting feature is that S4, which is the critical, the problematic state, is usually reached from S3, though not that often because it's only 6% of the time. To some extent, S3, well, Hirdesh likes to say, I mean, the main author of the paper likes to say that S3 is a precursor. I would rather say that it's something that indicates that something may go wrong because you might go to S4, which is definitely a state usually identified with crisis. Similarly here, the Japan setup. So all this research was done basically by Hirdesh Farazi et al., published in New Journal of Physics. An interesting fact, of course, rates do not obey detailed balance, so you are definitely outside of equilibrium. Whatever you have here is strongly out of equilibrium. An interesting check from the transition rates, and if you assume that you're dealing with a Markov process, you can, of course, trivially get the occupation numbers for the 4 or 5 states, the occupation probability. That's a steady state calculation, 4 linear equations in 4 unknowns. And what is striking is that to 2 decimals, to an accuracy which you absolutely would not expect, the results, the empirical probability and the predicted ones by the Markov model coincide. Now about vanishing eigenvalues, I want to say quickly something about the emergent spectrum. So when you apply this dreadful transformation called the power map to something that has 380 zero eigenvalues, what happens? Well, one of the things that happens is that, of course, none of the 0 eigenvalues remains 0. So you have they blossom to a full spectrum of 380. But if Q is close to 1, and this is now what we're going to take not Q equals 1.6, but Q equal 1.0001, then, of course, you have 2 spectra, one which arose from the 0 spectrum, and the other one which is the normal noise hump. So let me show you quickly a couple of pictures. So this is if you have a correlation matrix which is purely random and has no real correlation. Then what you see is that you have the well-known hump on the left, so to speak, for